Hi everybody, welcome to AP Chem video. This is Mrs. Hanson. Thanks for coming back. I hope the sound is better. Well, today's topic is redox reactions. This is one of mine and Ms. Schneider's absolute favorite topics. Now redox reaction, well the key is that all redox reactions involve electron transfer. We're going to see what that means in just a few minutes. Now redox reactions, they're actually not new at all. We've been talking about them all along, we just haven't used this term before. All combustion, all single replacement, no exceptions, lots of decomposition and synthesis reactions, and even some double replacement reactions are actually redox reactions. Okay, now how are we going to identify which ones are redox, which ones are not? The key is that there's this change in oxidation number, or sometimes we say oxidation states. Okay, now what the heck is an oxidation number? Well, it's really just this kind of bookkeeping method for keeping track of electrons during a reaction. Okay, now an oxidation number by definition is this guy right here. It represents the charge an atom would have in a molecule or compound if the electrons were transferred completely. Okay, and you're going to see that there's some rules. Okay, these rules for determining oxidation numbers, a lot of them are very logical. Some are a little bit weird. So let's take a look at them. So this first bullet, an atom in a neutral, an atom that's neutral, or it's just a free element, its oxidation number would be 0. So if I'm just sitting there looking at sodium metal, okay, it's not a sodium ion, just pure, silvery, shiny silver metal, it would have an oxidation state of 0, okay? How about O2 gas? So we're talking about oxygen in the air, not in a compound, just free elemental oxygen, oxidation state 0. Even a different form, an allotrope, you guys know that word? Allotrope. You hopefully remember that from regular chem, but an allotrope is a different form of the same element. So O2 and O3 are allotropes of oxygen. O3, it's still just that free element by itself. Okay, so oxidation state, 0. And even like mercury liquid, oxidation state 0. Okay? Okay, so that makes sense. So an element by itself in its elemental form has an oxidation state of 0. Okay, a monoatomic. So mono means 1. Okay, atomic means 1 atom. Okay, a monoatomic ion, its oxidation state is exactly the same as its charge. So for instance, a sodium ion is Na+. It's 1 element, 1 atom, has a plus charge. So guess what? Its oxidation state would be a +1. Sorry, didn't mean to cough on you. Okay, I don't think it's contagious. So what about Cl-? Monoatomic. It's 1 atom, has a -1 charge. Okay, H+, same thing. So the charge equals the oxidation state. So that's super easy, no problem. All right, fluorine. Fluorine, there's no exception, is always a -1 in every compound. Okay, so if you have H and F, fluorine would have a -1, which you would expect. Okay, the hydrogen, then you can figure out the other one will be a +1. Okay, can you guys hear that announcement? Sorry. Okay, I hope you guys can hear me okay. So what about this one, PF3? We know for sure that fluorine is a -1. We're not sure about phosphorus, but we can figure that one out based on what fluorine is. So if fluorine is a -1, there's a total of a -3 because there's 3 of them. So that would mean phosphorus has to be, do you know, a +3. Okay? So it's kind of like process of elimination, or if you know one for sure, then you can figure out the other one. All right, oxygen is a little hazy. 95% of the time, oxygen is a -2, which you would expect because that's its common ion charge. Every once in a while, though, oxygen can take on a -1 charge. The time you would see that is when you see the peroxide ion. Now, peroxide, you've heard of hydrogen peroxide, but you probably didn't realize that hydrogen is an H+, peroxide is actually an ion, okay? And it's kind of a weird one. It's the O2 2- ion. So what that means is it's kind of like a diatomic ion in a sense. So 2 O's, and overall it has a -2 charge. Okay? So that means that each oxygen has to be a -1. And there's 2 of them, so together it equals that -2 charge. So take a look at water. -2 on the oxygen, so what does the hydrogen have to be? Okay, well each one's a +1, so that'd be a +2 overall. Okay? CO2. All right. We're going to assume that oxygen's a -2 like it usually is. -2. There's 2 oxygens, so that's a -4. So what's carbon have to be? It has to be a +4. okay? Now, this one looks a little weird. I forgot to mention this. How do you know you got the peroxide on? It will almost always be the oxygen to whatever it's bonded to in a 1-to-1 or 2-to-2 ratio, okay, to recognize the peroxide ion. So Na2O2, it's kind of like H2O2, right, like peroxide. So we know that sodium's a +1, okay, so there's 2 of them, so that's a +2 on the sodiums. So it has to be a -2 on the O's. There's 2 of them, so that means each oxygen is a -1, okay? So look for that like 2-to-2, and that's often a hint that it's going to be one of those peroxide ions, okay? Make sense? All right, so hydrogen. Hydrogen can go 2 ways. Hydrogen is always a +1 in covalent compounds, but it's a -1 when bonded to metals and hydrides, when bonded to metals. So let's take a look. Water, we did that one already. Oxygen was a -2, so the hydrogen was a +1, okay? This is a covalent compound. That makes sense. All right, now this one, this one's a little sticky. You got these 3 atoms, and which one do we know most confidently? Well, I might look at nitrogen and say, nitrogen, if I look on the periodic table, nitrogen commonly takes on a -3 charge. So that seems logical. So if nitrogen's a -3, and then it's a covalent compound. So hydrogen is going to be a +1. Plus, this is an acid, so we know that acids always start with an H+. So that makes sense. Carbon can be a little bit confusing. It can have lots of different oxidation states. But if nitrogen's a -3 and hydrogen's a +1, what's left? Carbon has to be a +2. So a +2 and a +1 adds up to a +3 to counter the -3 on nitrogen. Okay? All right, let's take a look at CH4. Covalent compound, right? All nonmetals. So we're going to assume that hydrogen's a +1. There's 4 of them, so that means a total of +4 on the hydrogen. So guess what carbon's going to be? A -4. Okay? So right there with these 2 examples, you can see carbon's a +2 in this example and a -4 in this example. And that's totally okay. You'll see a lot of variety with carbon. All right, now here's the weird one. This is sodium bonded to hydrogen. Well, actually, sodium we talked about earlier. This is an ionic compound. This is a monoatomic ion. It's just that sodium in ion form. Sodium's a +1, so its oxidation state's a +1. So that means hydrogen actually has to be the anion. So this is a case where hydrogen is going to be a -1. Okay, so take-home message, hydrogen is usually a +1 unless that hydrogen is bonded to a metal. Okay, then in that case, the hydrogen is going to be a -1. Good? All right, got a couple more rules. Don't worry. You guys will get very used to these rules. Now this one, we actually have to go back to something you guys learned in regular chem. It says the more electronegative element takes on the negative oxidation number. All right, so today or whenever you guys picked up this electronegativities table, okay, and I'm just going to remind you guys how it works, is that electronegativity, it's basically desire for electrons. Okay, so what elements on the periodic table absolutely 100% desire electrons? Well, hopefully you guys might remember that fluorine's the winner on that, okay? Fluorine's got 7 valence electrons, and it really, really, really wants that one more. So fluorine has the absolute highest electronegativity. Okay, notice that the noble gases aren't even on here. It's because they really don't have electronegativity values because they don't attract electrons at all, okay? So the basic trend is that electronegativity, it increases going across, okay? It increases going across, and then it decreases going down the periodic table, okay? So as you go down, they get less and less and less electronegative. For our purposes, what you need to know is that fluorine is the big dog. It has the absolute highest electronegativity, followed by oxygen, okay? And then nitrogen and chlorine coming in at 3.0 are next highest. So I sort of summarize that in your notes. I call it the fun trio. Fluorine, oxygen, and nitrogen are real electronegative. Okay, chlorine's actually tied with nitrogen. Okay, and then bromine, and these guys down at the end of the list. Okay, but these are probably the big ones that you want to remember. So how do you apply this? Well, take a look at these 2 compounds. You got iodine bonded to chlorine. You know you want to make one of these a -1 because that's the charge it would take on in normal compounds. But you can't make both of them a -1. So who's going to get the -1? So with iodine and chlorine, if you look at the periodic table, the electronegativities, as you go down the halogens, they get less and less and less electronegative, okay? So if you take a look, what were we comparing? I to Cl. Here's iodine, here's Cl. Cl is more electronegative. That means it's going to want the electrons more. So we're going to give chlorine the -1 charge. So now there's a -2 on the chlorines. So what's that leave for iodine? How about a +2? Make sense? What about this guy? Now, what do you know for sure? Let's see. How about the hydrogen? It's a weak acid. It's sitting out there in front. Yes, hydrogen is a +1. Now these two. Who's more electronegative? Oxygen or chlorine? So you go back. Oxygen is the second most electronegative element on the periodic table. So we're going to give oxygen its usual minus charge, which is a -2. What's that leave for chlorine? So -2 on the oxygen, +1 on the hydrogen. So how about a +1 on the chlorine? See how that balances out? Now, one thing that is kind of obvious, I hope, but I'll say it out loud just to make sure, is that this compound is neutral overall. So a -2 and a +2 cancels out to make a neutral molecule overall for this one. Okay? All right, so that looks good. And by the way, this goes back to how oxidation numbers are kind of a bookkeeping method, but it's not a realistic thing. Because if you look at this compound, it's completely covalent. It's sharing of electrons. But for oxidation numbers, we assume that it's behaving like an ionic compound. And that's kind of weird. But that's what oxidation states are all about, and you're going to see how that helps us when we start looking at, what a redox reaction is as a whole, okay? But we are saying that the chlorine is actually stealing electrons from the iodine like an ionic compound. Not really the case because it's really covalent and it's really sharing, okay? So just keep that in mind. This next rule, the sum of the oxidation states for the entire compound or ion has to equal the oxidation states added together. Okay, we kind of already talked about that with this neutral compound, but these guys have ion charges. So let's see, chlorine and oxygen. I'm going to say oxygen's going to have the negative charge, so we're going to give it its usual -2. Okay, 4 times a -2 is a -8 on the oxygens. Here's the thing. The whole compound, or ion in this case, has to add up to a -1. So what's that mean chlorine is? Let's see, there's 1 chlorine, and overall it's a -1, so it has to be a +7. Okay? So keep that in mind with your ions. What about the ammonium ion? Let's see, hydrogen. See, it's not bonded to a metal, so we're going to keep hydrogen as a +1. All right, and there's 4 of them, so that's a +4. And it has to be a +1 overall. So what's that leave for the nitrogen? Nitrogen's going to have to be a -3. Okay, a -3 and a +4 ends up giving you that overall +1 charge. Okay? All right, guys, you're doing great. We're almost done. This one's really weird. This does not come up very often. But oxidation numbers do not have to be whole numbers. What? Take a look at this example. Which one do you absolutely know for sure? I hope you said sodium. Sodium is a +1, so that means that the oxygens have to be a -1 overall. Well, how do you get 2 oxygens to add up to a -1? Okay, if this is what you're thinking, you're correct. Each oxygen is a -1/2. Whoa! So the oxidation state on that oxygen is a -1/2 for each of the oxygens. Together, a 0.5 and a 0.5 basically adds up to a -1. Okay, now that's weird. That's the superoxide. Do not see it often, but it does exist, and it can happen. Okay. Let's see. Metallic atoms always have positive oxidation numbers, never negative. Seems pretty logical. Metals like to give up electrons. They like to lose electrons. An atom can never, I love this rule, can never have a higher oxidation state or number than its number of valence electrons. Okay, let's see what this means. ClO5 minus ion. So let's say oxygen, -2. So that puts a -10 on the oxygens. Overall, let's see, the whole molecule has to add up to a -1. So what's that mean chlorine is? It means chlorine's a +9. Guess what? Cannot happen. This molecule does not exist. No. Because if you look at chlorine on your periodic table, okay, chlorine's in the 7th family. It has 7 valence electrons. You knew that. So you guys remember this oxidation state is you're pretending it's ionic. Well, chlorine can't lose 9 electrons. It can only lose a max of 7. Okay, so that's why that rule exists. Okay, so chlorine only has 7 valence electrons, plus 9 is not reasonable. Okay, love that question. We always catch students on little multiple choice questions with that one. All right, well, guess what? It's your turn. So what I want you to do is pause the video, do it, and I want you to give these a try. Take like 5 minutes using the rules, and then resume the video. Okay, do it, do it. Okay, so let's talk about how you did on this. So hydrogen, now this is hydrogen bonded to aluminum, so this is a hydride. Hydrogen's a -1, -3 overall, that makes aluminum a +3. Good. Oxygen, -2, so it's a -8 overall on the oxygens. Potassium, of course, is a +1 because it's a monoatomic ion. So what's that leave for manganese? That makes it a +7. Okay? You guys are doing good. This one's kind of a tough one. Hydrogen's a +1. There's 2 of them, so that's a +2. Okay? Oxygen, -2, so it's a -8. So what's that leave for carbon? Let's see. Well, it's going to leave a +6 overall, but there's 2 of them. So that means each carbon is going to be a +3. So just keep in mind that these are the oxidation states. Okay, this is just our math to help us figure out these are the oxidation states on each of those elements. All right, how about this weird guy? Okay, tungstenate ion, if you will. Let's see, so -2 on the oxygen, so it's a -8. -2 overall. So what's that mean tungsten is? Must be a +6. Okay. And you guys might, did you have this compound in your notes? If you did, just kind of ignore this part and we'll just focus on the tungsten part, or the WO4 2- part, okay? P4, oh, don't be tricked by this one. It is just that element and it does not have a charge. It's in its elemental form, 0. Bam, okay? Fluorine, always, 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 -1. So that's a -4. Okay, now, what do I know? Xenon, didn't even know xenon could make compounds. It can, not very many, but it can. Oxygen, well, pretty safe to assume that's a -2. This isn't like a peroxide situation. So that's a -6 so far, so xenon actually has to be a +6. And that's okay, because xenon has 8 valence electrons, so we haven't gone over that, which is good. Now, I3, oh, that is not an element by itself because it has that ion charge. It's an ion. So guess what? It's not 0. Okay? Okay, so I got a -1 overall. 3 iodines have to add up to that. Well, if you said -1/3, you would be correct. Each one of those ions is a -1/3, adds up to a -1 overall. Tricky. I like that one. Fluorine, -1, more electronegative, so -3, so the iodine has to be a +3. How did you do? I hope you guys got them all right. Okay, let's go ahead and take a look at this one. All of these have nitrogen in them. So again, pause, do it yourself, and then resume and see if you got it right. Okay, pausing. Okay, resume play. So let's see. -3, well, lithium, of course, is going to be a +1, so it's a +3 overall. So nitrogen's a, whoops, sorry about that, is a -3. Let's see, hydrogen. Ooh, tricky one. How do you guys decide this one? If you look at this one, you got nitrogen and you got hydrogen. Nitrogen, ooh, let's come back to that one. I don't want to hold up the video. Oxygen, a -2. So what are your nitrogens going to add up to be? A +2. So each nitrogen has to be a +1. This oxygen, -2, so -4. So this nitrogen is a +4. Okay. Let's see, -2 on this oxygen, which is a -4, equals -1 overall, so this one has to be a +3. And finally, this guy, oxygen, -2, so that's a -6. Okay, equals -1 overall, so guess what? This guy's a +5. Okay, this one, a little bit hazy. This one, nitrogen and hydrogen, which one's more electronegative is definitely the nitrogen. Okay, so we're going to make that nitrogen have the negative charge. Where'd it go? Okay, so we'll put the hydrogen as a positive, so it's a +4. Okay, then what's each nitrogen have to be? A -2. Okay, I'll be honest, I just had that wrong in my notes, so I had to think about it for a second. Does that look all right to you guys? Make sure it's right. Okay, great. Right, you guys are doing wonderful. Now let's see, what are we going to do with these rules, okay? Well, we're going to start looking at redox reactions, okay? Redox means it involves reduction and also oxidation. It's two separate processes that both happen in one redox reaction. So, oxidation is the process of losing electrons, okay? Reduction is a process of gaining electrons. Both of them are going to happen in one reaction, okay? Now, this is so important. Absolutely the essence of what you got to remember. How can I help you remember that? Okay, and I always remember something called oil rig. Okay, oil rig. Oxidation involves loss. Okay, so oxidation is losing. Reduction involves gain. Okay, or some people, like Leo says, grr. That one's catchy too. Losing electrons, oxidation. Gaining electrons, reduction. We're going to have a vote in class. We're going to see which one you guys like better. Okay, but oxidation is losing, reduction is gaining. So let's actually look at a reaction that we have here. So we got zinc reacting with copper sulfate, classic single replacement reaction. What I want you to do is determine the oxidation states for each element that's involved here. So zinc, element by itself, no charge, 0. Okay. Copper sulfate. This is an ionic compound, so let's see. I'd probably start with oxygen because I feel pretty confident on that. -2, that's a -8 on the oxygen. Okay. And copper, you know, it's bonded to sulfate, right? Sulfate's a -2 overall. So what's copper have to be? A +2. And that's okay because it's just that ion by itself, so it's got a +2 charge. Charge equals oxidation state in that case. What's that leave for that silly little sulfur in the middle? So let's say we got a -8 and we got a +2, so that leaves a +6 for the sulfur. Okay? Do the same thing with zinc sulfate. Now, interestingly enough, the sulfate hasn't changed at all. That usually means its oxidation state will not change at all. So -2, -8, and again, zinc is a +2, so sulfur is still a +6. But copper, no charge, all by itself is 0. All right, so looking at the reaction overall, what's being oxidized, what's being reduced? Let's see, zinc is going from 0 to +2. 0 to +2. So that means that zinc is losing electrons, right? That would be the process of oxidation, losing electrons. So the zinc atom is being oxidized into zinc 2+. All right, well, if one thing's oxidized, something else has to be reduced. So let's see. The only other thing changing its oxidation state is the copper. Here it's a +2, and here it's a 0. So you know what? The copper is gaining electrons. It's gaining electrons to go from +2 to 0. So it is being reduced. So this would be the reduction part of the redox reaction. Okay? All right. Nothing else is changing, so we are good to go. Little terminology. The oxidizing agent. Okay? Now, whatever species is being oxidized, sorry, you know what? Let me fix that. Whatever species is being reduced is the oxidizing agent. Okay? So whichever ion or molecule is gaining electrons, right, being reduced, gaining electrons, is allowing for something else to lose or to be oxidized. So it's kind of like opposite world, okay? So the oxidizing agent is the one being reduced. So which species, which just means which part of the reactants, is the oxidizing agent? Well, what guy is actually being reduced? That would be the copper sulfate, okay? By the copper sulfate gaining electrons, it's taking them from the zinc, causing it to be oxidized. Okay? So don't worry, you'll get used to it. We try not to use these agent terms too much because it's a little confusing, but you got to be familiar with it. So what about the reducing agent? Whatever species, well, of course, it's going to be opposite, so let me correct that. Whatever species is being oxidized, a little bit of opposite world. So whichever ion or molecule or whatever is losing electrons, okay, it's going to allow for something else to gain or something else to be reduced. So what entity or what species is the reducing agent? Okay, well, who's losing the electrons, allowing something else to be reduced? That would be the zinc metal. Okay, so there you go. What I want you to do, and have this done for tomorrow, or whenever, by Tuesday, is I want you to go ahead and look at these reactions, A, B, and C, and I want you to decide, is it redox, yes or no? Okay, so do you see a change in the oxidation numbers? Of the 3 reactions, okay, 2 of them are redox and 1 is not. And then I want you to identify specifically what element is being reduced and what element is being oxidized. Have this done for class, okay? For us, it's due Tuesday. All right, any questions? You can ask in class. Thank you for listening. Have a wonderful, wonderful day.